Uncertainty is everywhere. It lurks in every consideration of the future. The weather, the bats, and even things we think we know contains the possibility of an error.
Over the centuries, driven by curiosity, competition, and desire, pioneering mathematicians and scientists began to reduce world uncertainties to tame distributions of probability and statistical inferences.
Even as the unknown became known, we still believe that some problems were unsolvable, and our intuition misled us.
As we realize how omnipresent and varied uncertainty is, we encountered chaos, quantum mechanics, and the limitation of our predictive power. But one thing is clear: a reasonable probability is the only certainty.
In this episode, we're going to review Chapter 8 of the book Nature's Numbers by Ian Stewart, entitled Do Dice Play God? We're gonna delve deeper into various theories and concepts as well as their applications in our everyday lives.
And for Pierre-Simon de Laplace, his idea of determinism is the belief that the past completely determines the future, that we may regard the present state of the universe as the effect of its past and the cause of its future. These concepts produce an image of a totally deterministic world, one leaving no room for the operation of chance. However, many encounters in our daily lives seem purely occurring by chance or lady luck, such as finding money along the way or bumping into an old friend. By this, it seems it's not so much a universe in which, as Albert Einstein memorably refused to believe, God plays dice. It seems more a universe in which dice play God. The intellectual legacy of Isaac Newton was a vision of a clockwork universe. It is an image of the universe as a mechanical clock, set in motion at the instant of creation and thereafter running in prescribed rhythm that requires no further interference, making every aspect predictable.
To further understand the mentioned concept, first let's utilize probability of outcomes in a dice. When a single die is thrown, there are 6 possible outcomes because a dice has only 6 sides, and at every throw, there is only one outcome, which means the probability of each outcome is 1 over 6. This example implies that we can only guess the probability, but we cannot still accurately determine which side of the dice will come out in every throw, because in every throw, the outcome may vary without a pattern. Another example is the water drop system that was conducted by a group of students from the University of California, in which they tried to record and predict the intervals between each water drop, and as a result, they only discover a short-term predictability. For instance, I know the initial 3 drops to an accuracy of 10 decimal places. However, after some time and several drops, the accuracy decreases and the error increases. In that case, it will be impossible to accurately predict the timing of the following water drops in the future.
On the other hand, to predict the future behavior of an object, Henry Poincaré created a diagram that shows what happens for all initial values, as recorded by the movement of objects. Each pair of initial values generate a new curve, allowing us to capture all of a system's conceivable behaviors. A series of curves whirls around a plane known as a system's phase space, a geometric visual scheme of points flowing through the space of both populations. To predict how a system will behave in the future, both its position and momentum must be known. Indeed, this concept represents an advancement because instead of worrying about the precise numerical details of an equation solution, we may concentrate on broadening the phase portrait. Moreover, the word prediction has 2 meanings. One is foretelling the future, and the butterfly effect prevents this when chaos is present, but the other is describing in advance what the outcome of an experiment will be.
At this time, in relation to chaos, the butterfly effect is dependent on initial condition in which a small change in one state of deterministic nonlinear system can result in a large differences in a later state. Lawrence, a mathematician and meteorologist, noted that butterfly effect is derived from the metaphorical example of the details of a tornado being influenced by a minor perturbations such as a distant butterfly flapping its wings several weeks earlier. Lawrence discovered the effect when he observed runs of his weather model with initial condition data that were rounded in a seemingly inconsequential manner. He noted that the weather model would fail to reproduce the results of runs with the unrounded initial condition data. A very small change in initial conditions had created a significantly different outcomes. In shorter definition, the butterfly effect concept has since been used outside the context of weather science as a broad term for any situation where a small change is supposed to be the cause of larger consequences. The butterfly effect presents an obvious challenge to prediction, since initial conditions for a system such as the weather can never be known to complete accuracy. This problem motivated the development of ensemble forecasting, in which a number of forecasts are made from perturbed initial conditions. Thus, the sensitivity of these systems' outcomes are unpredictable. This idea became the basis for a branch of mathematics known as chaos theory.
Chaos theory is an evolutionary theory that describes how a system goes from order to disorder unexpectedly. It is a method that combines qualitative and quantitative analysis to explore dynamics. It is used to talk about dynamic systems that need to be integrated and continuous rather than just a single data relationship to describe and anticipate behavior. This idea gave way to the formulation of chaos control from the basic principles of the chaos theory. Chaos control is a practical technique wherein small changes in the starting settings can result in large changes in subsequent behavior. It is the boundary field between control theory and the dynamic systems theory, studying when and how it is possible to control systems exhibiting irregular and chaotic behavior. All of the concepts that we tackled, such as Laplace's determinism theory, Poincare's phase space theory, water drop system, butterfly effect, and chaos control, explain that as of now, there are concepts and events that can be predicted based on the given data and scientific knowledge that we have. But there will always be something which we cannot predict based on our current knowledge. A perfect example would be the random decay of radioactive atoms, wherein up until today, we still do not have any statistical or scientific prediction on what would happen to them. Thus, the question remains on whether unpredictable things can be left to God and Lady Luck, or will humans be able to unlock the code in predicting the future and altering it for ourselves. Once again, this has been group number 8, and I hope you had a good day. Thank you so much.